this set of premises, and sometimes you do have to introduce ad hoc hypotheses to protect this hardcore, and it is okay to do so when these ad hoc hypotheses explain data that you did not have an explanation for. They're even better if they predict data that you are able to actually observe, and then you are on a progressive research program. But if you have to introduce ad hoc hypotheses that only explain data that did not have an explanation, they don't predict any new data. And even if they do predict, you cannot observe them, then you're going on the degenerating side of your scientific research. And then a new paradigm is sort of called for. Feyerabend is the least orthodox in this group. He really thinks that the rational mind is not creative. He understands that rationality really brings too many limitations to the scientific endeavor, that it limits your creativity, it limits your possibility of looking for new alternatives. So he really says that scientists should go irrational. They have to trust their inspiration. There are no general methods, according to Feyerabend, that there are at the most heuristics. And this is kind of interesting. When I first read this, this was what really attracted my attention when I first started studying philosophy of science. And later on in my career, I came across Professor Chaitin, and that was when we were talking about this subject. And he said, well, yes, in mathematics, this is actually a theorem. This is not just something that a certain philosopher thinks about philosophy of science. You can actually prove that within a closed system, you cannot actually put forward anything that is actually new and creative. So the difference between our view and Feyerabend's view is that Feyerabend calls this irrational. It is irrational for Feyerabend to actually extrapolate from the existing rules. He says you need a kind of an explainable step to do that. Whereas we just think that all you have to do is use your creativity, maybe a little bit of inspiration, but that doesn't mean it's completely irrational in the sense that you didn't have to think and ponder about it. And what you actually have is rationality rules. So you don't have to believe that science is either rational or irrational, and that there are irrational periods in science, but there are periods in science when you're changing irrationality rules. And there are rules and principles, right? In this what defines the rationality for your paradigm. There are plenty of them. I'm just citing a couple so that you get a feeling of what we're talking about. So you can choose the ontology you want to work with. You can choose the language, the kind of language you want to work with. Your epistemic goals are also very important. Can everybody see? The methods and techniques you're going to employ, and your conceptual framework, that is basically your vocabulary. Your vocabulary is very, very important because, in our view, the concepts you choose and the concepts that come up in your research have a lot to say of what is the ontological level of your research. These things you don't actually wake up in the morning and decide, I'm going to use this ontology, I'm going to use this vocabulary, I'm going to use this kind of language. This is something that builds up as you are doing your research. I think you probably almost have had this experience. And of course, rationality principles and rules do change in paradigm shifts, and they're also different between in different areas of the scientific realm. So the business of questioning if social sciences are not scientific here has a different dimension, because what we would say is that, yes, the social sciences do sometimes have different rules and principles of rationality. Now, metabiology in this scene really appears as an interdisciplinary paradigm shift, because it is built from theoretical biology and biology and algorithmic information theory. So when Professor Chaitin says that he is entertaining life as randomly mutating and evolving software, and when he says that nature is programming, he is really doing a paradigm shift, and it is actually very interdisciplinary because, as we will see, and as you have seen already, it uses a vocabulary, it uses an ontology, it uses a conceptual framework that really comes from different areas in science. So there is a change of the basic concept from energy to information in explaining what life is about. The process is different, therefore, from metabolism to algorithm. The language is also different from continuous to discrete, post-Gödelian math. The methods are different. Professor Chaitin is a mathematician, and he really likes to prove theorems, and he thinks that this is what really gives you an understanding of the phenomenon you're studying. There is a change of the conceptual framework. There's a whole new interdisciplinary vocabulary that we're going to talk about. And there is a change in the epistemic goal. We're not explaining the biological behaviors given selective pressure. We are really trying to explain biological creativity.
Sorry, what do you mean by change of methods from simulation to mathematical proof?
Yes, because although there is this idea of maybe making simulations based on metabiology. Metabiology really started off with mathematical proofs. Professor Chaitin is not really interested in building the theory through simulations. He wants to build the theory through mathematical proofs. And from the mathematical proofs, maybe make adaptations and make simulations. But the theory is is more, if we think about the method, it's more a deductive than an inductive theory, because it really comes from proofs to simulations and not simulations trying to come up with a general explanation. Is that okay? So this is why the change in methods is the change in methods in how we came up with, how Professor Chaitin came up with metabiology.
But yesterday she was saying that...
Yes, you can. Yes, you can. Right, you can. You can. Yes, but you see, you can simulate based on the model that was achieved by proofs. First, you want to get to a model that you arrive at proving theorems. Then you can start simulating. Whereas in other areas of the application of math and computer science to biology, what you really do is that you do massive simulations to try to come up with a general pattern. Okay, so this is the basic method. It's not that you can't apply simulations, but the basic method for creating metabiology was really trying to get at a mathematical proof first. Okay, interdisciplinary research. This sometimes is really a complete mess. People get very confused, and some people really just reject interdisciplinary research because there is you feel uncomfortable with this invasion of ideas from another area. You feel uncomfortable because you don't really know what this new concept is bringing along with it, and every concept, as we know, points to another concept, and applying a given concept in a different conceptual network really sometimes doesn't work. You have to recreate this concept, and it has to be you have to find a new meaning for that concept in this new context. And this is sometimes tough, and sometimes people really feel uneasy with that. So this is why in the proposal we have for interdisciplinary studies, we really like to think that the concepts, when they migrate from one area to another, it's really a non-isomorphic migration. The concepts do not remain the same. So an algorithm in algorithmic information theory is not exactly the same as the algorithm in metabiology, although they have great resemblances, but it's not really exactly the same thing. We chose the name mimetic. Mimesis is a word that really comes from philosophy. It has a great history in philosophy. I don't think I have to tell you too much about it, but what it comes down to here is that when you do a mimesis on a concept, you really have to think about how it changes its meaning and how it may change its connections to the conceptual vicinity that it had in the original field. And the way that we have found methodologically to distinguish between just a useful analogy or an interesting or colorful metaphor that is very often used in science and in philosophy to really a conceptual migration is that you are going to see if you can migrate the conceptual vicinity as well as a concept that you first thought about, which in the case of metabiology is DNA and a computer program, if you can get the conceptual vicinity around DNA and around the computer program, and will they actually make sense when you start trying to match them. So this is how we have sort of like a validation criterion for a mimetic migration, and the making sense is also sometimes a challenge because it's not the sense in either one of the original areas. It's a new sense that you are creating in metabiology. So this would be maybe the basic concepts. It's tough to choose, but when I was building this presentation, I was thinking of really bringing